Hi, I'm Pietro Centorrino, and I'm here to present model and optimization of visitors flow in crowded museum. This is part of a work that is being published in Journal of Computational Science this year and is co-authored with Alessandro Corbetta, Emiliano Cristiani, and Elia Onofri. The first thing we need to ask ourselves is why we need to understand visitors' behavior. We are currently living in a pandemic situation, so understand how crowds move inside a museum and how they distribute in a room is fundamental for social distancing. Beside the emergency situation, this information is crucial to well organize the museum to prevent overcrowding, and understand how crowds moves is also a key factor to address the complex dynamics during evacuation. Also, the presence of humans is directly linked to the increase in temperature and humidity inside the museum, parameters that must be controlled in order not to damage the works of art. Then we have the individual behavior. We have the organization of the visit. The visitors move following the curator instruction. The audio guide is too short or too long. Which kind of visitors are present in the museum? This information can be very useful to the curator and to be answered that need the understanding of individual behavior, which also can give insight about the most difficult to answer among these questions: how humans enjoy art. We do not want to answer all these questions, of course. So in our we cannot answer all these questions, of course. So in our study, we point four steps in order to manage the visitors' flow. The first one is to track and observe visitors. We did this with Bluetooth device. Then, once the trajectories are available, we try to understand the visitor's behavior. And we try to recreate this behavior with a digital twin of the museum. Once the digital twin is validated, we can try to use it to optimize the visitor's flow. In particular, we are proud of these results since recently Galleria Borghese, our case study, adopted our proposed methodologies, actually providing more than a proof of concept to our work. Our case study, Galleria Borghese, contains some of the most famous masterpieces in the world. There is a room full of Caravaggio and statues by Bernini and Canova. Also is an historical building and is very small. For this reason, in some rooms there's problem of overcrowding. The museum is organized as follows: have 2 hours time slots and there's mandatory exit at the end of the slot, 360 visitors for turn, and we collect 70 trajectories from turn, 900 trajectories in total. The trajectories are Lagrangian coordinates with room precision. So, how we collect these trajectories? Our measurement system is very easy to implement and is based on small beacons that we give to visitors at the entrance. These beacons send a Bluetooth signal that is being received by Raspberry Pi antennas with a RSSI, so a strength indicator of the signal, plus a timestamp of the reception of the signal. All these data are collected in a central server. The pro of this system is that it's not invasive. We do not ask for the identity or ask to install an app on their device to the visitors, and also is very cheap. Of course, there's some problem. The RSSI signal is very noisy, so visitors can be detected by multiple antennas or not detected at all. As you can see in this very confusing graph, where each different shape is a different antenna and the height is the intensity of the signal. In some case, you can see the visitor that jump in between rooms, and this is clearly a not realistic behavior. So how we solve this problem? To overcome this problem, we try three different methods to reconstruct the trajectories. One, where we just check the maximum of the signal, and as you can see, it's not very precise. Then we try a moving average, which well perform on transition from a room to another, and then we try a neural network, which outperform the other method, especially in estimating the time of permanence inside rooms. I will not go deep in this argument since my colleague Leah will talk more in depth about this topic in another presentation of this conference. I will put a link down in the description. Once the trajectories are reconstructed, it's possible to clusterize the set of data in order to understand preferred paths of visits or type of visitors. We use an unweighted method, so at the beginning, each cluster is identified by a representative trajectory, and there is the same number of trajectories and cluster. Then, a Wasserstein distance is evaluated between representative trajectory, and via dendrogram, the nearest cluster from a Wasserstein point of view are merged together. The new representative trajectory will be a topological average of all trajectories in the cluster. At the end of this process, the representative trajectories of the numerous cluster will be the preferred path on the museum, and surprisingly are similar to the real ones. This was not to be taken for granted, considering that we had not imposed any type of control in the clustering. Another important feature to analyze and to get insight about the visitor's behavior is the time of permanence inside rooms. We fit our data via Weibull distribution, and we use both this fit as an analytical tool for the simulation and also to gain information about room popularity, looking at two parameters of the distribution. One is lambda, which is a characteristic time, and then k. If k is equal to 1, we have a Poissonian process, meaning that the decision to leave the room is completely random. Instead, we observe in all our room k bigger than 1, attending for an aging process, so that the probability to leave the room increase with time, probably because Galleria Borghese is very dense of artwork. The more attentive of you will have noticed that the last picture is not well fitted, and this is the distribution of the time of visit of the museum, which in our case study is affected by the forced exit. We will come back in this problem later since this factor was critical to the success of our model in our case study, which we are going to talk about now. So, the goals of our visit model is to recreate both individual and collective behavior, so simulate realistic trajectories and also recreate correct time series of person per room. There's problem in doing that because the path of visit are not linear because there's a not suggested path, and also the number of person per room is not at equilibrium. So our model is based on a Markov chain on graph, where the nodes of the graph is the room or the wings of the museum. The links are weighted with the measured transition probability between rooms that we calculate from real trajectories. The model, though, is based on three assumptions. We do not take in account the influence of other visitors. This is a limit of our model, but we found very difficult to implement this fact and not so informative in previous study. Then, group of visitors moves together, and we base this on our observation of the field. And then, in contrast with other previous study that use Markov chain approach, we impose that visitors have memory. Considering that Galleria Borghese do not impose a preferred path and visitor can walk through the museum in both directions, if we not take in account some sort of memory, we obtain a bounce effect. As you can see from the first test of the model, visitors without memory bounce between the same initial rooms and do not explore the whole museum. use a memory in our virtual visitors, a memory of the time spent in each room. We did this by weighting with a time-dependent function the probability of transition between rooms. This function is the survival function of the Weibull distribution associated to the room. So each time step of our simulation, transition probabilities vary according to the time spent by the virtual visitor in each room. A critical factor of our simulation is how visitors decide to exit from the museum. If the total number of visitors in the museum is not correctly reproduced, all the values of person per room will be affected. So the best solution we found is to control the out of the museum as a different state of the chain. We control the exit choice each step of the simulation via the hazard function of the total time of visit distribution, the whole time spent in the museum. Here, the problem of the forced exit was crucial in our case study, so we correct this function censoring the last 5 minutes of visit. We generate in parallel all the different trajectories and then we agglomerate them so that a single trajectory is assigned to a random number of visitors between 1 and 6 to form virtual group of visitors that visit the museum together. So, as shown is a very simple and general agent-based model, but let's see the result. Our model, although very simple, produces realistic trajectories, similar in terms of number of visited rooms, order of visit, equal average time of permanence, and similar variability. We also clusterize the simulated trajectory, as previously mentioned, and the representative of the numerous cluster is very similar. Then, of course, there's some difference. When virtual visitors arrive in an already visited room, follow the anti-clockwise direction while real ones generally come back following the guide instructions. While regarding room occupancy, time series of person per room of our simulated data are within the variability measured in the museum, and this is true for most of the rooms and for the museum as a whole, and this validates definitely our model in terms of room occupancy. Once the model was validated, we used it to imagine a better entrance system, with the aim of reducing overcrowding in the rooms, but without reducing the number of tickets sold. We tried two different systems. First, we vary the room of entrance percentage, so that there are three different entrance doors, and we discovered that the system that Galleria Borghese used was already the better ones. So we attack the problem from another point of view. We remove the forced exit from our simulation and we reduce the interval between entrance. So this drastically improved the visit experience. For the same number of visitors, there's overcrowding always under the threshold, less fluctuation in the room occupancy, and also less queues at the beginning of the visit. This is a great result for us, but also for Galleria Borghese, because the museum used the simulation to estimate the number of people to let enter inside the museum in COVID pandemic, but also after some tests on the field, used the model to change a 20 years old entrance system. No more emptying of the museum with mandatory exit, increase the number of visitors per day, but with less overcrowding and less queues. So this is a demonstration of the effectiveness of our approach. Thanks for your attention.